Good afternoon. This is your 9th digital class for the subject physics. Now in last class we discussed about the application of Gauss's theorem. So let me continue the topic because you do have few applications. Already you have discussed two applications. You do have more two applications. Now the third application which you are going to discuss is your electric field intensity due to a uniformly charged thin spherical shell. Okay, now what is shell? Shell is a sphere, you can say hollow sphere. Okay, if you take a hollow sphere, then it becomes a shell. So basically in shell what happened, the charges resides only on the surface. So let me draw a diagram. So this is your spherical shell, the solid one. Now you have to define field intensity at a specific point here. Now if you have to define the field intensity at this point, what you have to do, you have to construct a Gaussian surface, and that surface must have to pass through that specific point where we have to define the field intensity. Now you can give the name at this point as your P. I have not given here. Now if you have to define field intensity at this point, you have to consider a small element around that point. Now this element has an area ds. Now if you have to define the direction of this element, then you have to draw one normal. This is your ds vector. Now as it is positive charge, so field will be outward, so E vector and ds vector, they are in same direction. Now Gauss's theorem is your what? Total flux through any closed surface is 1 epsilon times the charge enclosed by the surface. So here if you consider at this point where you have to define the field intensity, then at that point the ds vector and E vector, they are in same direction. ds is nothing but the small elemental area from the Gaussian surface where you have to define the field intensity. So E vector and ds vector, they are in same direction at this point. So if you have to apply here in Gauss's theorem, so E ds cos 0 degree equal to q by epsilon naught. So cos 0 1, so E ds. So field intensity is same throughout the Gaussian surface, because Gaussian surface can be defined as an imaginary surface at every point of which the field intensity remains same. This one we have defined in our previous class. So E comes out from the integral sign, you do have ds only. So ds, if you have to define the area of this Gaussian surface, it is nothing but is your 4 pi r square. The Gaussian surface has a radius r, and the solid means hollow sphere, hollow spherical shell has a radius capital R. So you are defining the field intensity outside the spherical shell. So E equal to E 4 pi r square q by epsilon naught. So if you simplify, E equal to q by 4 pi epsilon r square. Now as the charge resides only on the surface, then you have to consider the surface charge density. So if sigma be the surface charge density, then sigma equal to charge by area. So area is your spherical shell area is your 4 pi r square. So q charge resides on the surface, so q by 4 pi r square gives you the surface charge density. So you substitute it here. If you substitute q, then sigma 4 pi r square. So if you simplify, it becomes easier r square sigma epsilon naught small r square. So this is the expression for the field intensity outside the spherical shell. Now if you have to define the field intensity on the surface of the spherical shell, then what you have to do, you have to you have to equate small r as your capital R. So if you substitute in this relation small r equal to capital R, then it becomes your sigma by epsilon naught. So this is the field intensity on the surface of the spherical shell. Now if you have to define the field intensity inside the spherical shell, then what you have to do, here is your small r less than capital R. So this is the diagram. This is your spherical shell, and this one is your Gaussian surface, and at this point you have to define the field intensity. Now basically what happened, inside the spherical shell there is no charge. Charge does not reside. So if charge does not reside, then q equal to 0. So if q equal to 0, then you can use Gauss's theorem where q equal to 0. So ultimately you will get what? E equal to 0. So you can say that there is no field inside the spherical shell. Now you do have three equations. One is your on the outside the spherical shell, which you define by equation 2. Another one is on the spherical shell, surface, small r equal to capital R, and third one is your r less than capital R, so it is inside the shell. Now you can draw this expression in the graph, and the graph is like this. This is your spherical shell and this is your field axis, this is your distance axis. So as there is no field as there is no field inside the spherical shell, so you can consider no graph 0 to r. I have not drawn any graph here, so field is 0. Now at small r equal to capital R, you do have a field that is the maximum value, and the maximum value is your sigma by epsilon naught. Now if you go beyond capital R, then field decreases with respect to small r. So as r increases, field decreases. So maximum value of field is on the surface of the spherical shell itself. So this is very important topic. Sometime in exam it is asked, find the field intensity in defined region of a spherical shell using Gauss's theorem. Now next one, we are trying to define electric field intensity due to a uniformly charged non-conducting solid sphere. So here also what you have to do, you have to consider this one as your solid sphere. Now what is the difference between solid sphere and spherical shell? In solid sphere there is a material inside the sphere, but in shell there is no material, it is hollow. So definitely charge resides inside the material of a solid sphere. So let me consider this diagram. This diagram is your this solid one is your solid sphere, and we are trying to define the field intensity outside the solid sphere. So at the point where you have to define the field intensity, we have to construct a Gaussian surface. This is dotted part is your Gaussian surface, and this is your solid sphere, and the charge resides here not only on the surface but inside the material also. So at the point where you have to define the field intensity, you have to construct a Gaussian surface in such a way such that that Gaussian surface must passes through that point. So around that point you have to consider a small element, so ds vector outward, and as it is positive, E also outward. So you have to go for Gauss's theorem. This Gauss's theorem is your close integral E vector dot ds vector. Now as E and ds both are in same direction, that's why cos 0 degree. So it is your E ds cos 0 degree. So you see E ds cos 0 degree, so q by epsilon naught. So E close integral ds q by epsilon naught. Now ds is your what? This one is Gaussian surface whose radius is smaller. So that is your 4 pi r square. So ultimately if you simplify, it comes out to be your q by 4 pi epsilon naught r square. Now as the charge is throughout the volume of the solid sphere, so you have to consider the volume charge density. If rho be the volume charge density, then rho equal to q by 4 pi 3 pi r cube. So if you have to substitute q here, then q equal to rho 4 by 3 pi r cube 4 pi epsilon naught r square. Now if you simplify this one, it comes out to be your r cube rho 3 epsilon naught r square. So this is the field intensity due to a solid charged sphere, uniformly charged non-conducting solid sphere outside the solid sphere. Now if you have to consider on the surface of the solid sphere, then you have to substitute as a small r equal to capital R, as you have seen in the diagram. The small r is on the Gaussian surface, and capital R is your radius of the solid sphere. So if the small r comes to the surface of the solid sphere, then it becomes your capital R. So whatever expression we have got for small r, if you substitute small r equal to capital R, then we will get r rho by 3 epsilon naught. Okay, now you see this one outside the solid sphere, the field is inversely proportional to r square. No, if r will be more, field decreases, and on the surface, if you go for this expression, it is independent of small r, it is capital R. If radius is more, then more field will be there. Now let me go for the third one, where small r less than capital R. So you see this is your solid sphere, charged solid sphere, charged throughout the volume. Now inside this one we have given solid sphere. Now we have constructed a Gaussian surface of radius small r, and this is your capital R radius. Now what happened if you have to define field intensity at this point, then you have to consider a small element. Let me consider the small element is your ds. So ds will be outward and field will be outward. So if you have to define field intensity at this point, then the expression will be your E equal to q dash 4 pi epsilon naught r square. Here what you have got here, in this case here we have got E equal to q by 4 pi epsilon naught r square. Q is the total charge on the solid sphere. But here if you consider this small portion of the solid sphere, then charge does not remain identical. Charge may be less, maybe not maybe, it's less definitely, because you are extracting a small portion of the charge solid sphere, so the available charge definitely less. That's why we have given q dash, otherwise the expression is identical. Okay, now definitely here small r is greater than capital R, and here small r is less than capital R. Now if you have to go for q dash, then q dash will be your rho equal to because q dash is the charge available inside the Gaussian surface, that is dotted one. So q dash is your 4 by 3 pi r cube. The volume of this one is your 4 by 3 pi r cube, small r cube. So if you substitute q dash here, then it comes out to be r rho 3 epsilon naught. And here you see that field intensity increases with the increase in r. If you consider a larger Gaussian surface inside the solid sphere, then field will be more, because if you consider the larger value of small r, then what will happen, more amount of charge accumulated inside the Gaussian surface, is not it? Because more the material inside the Gaussian surface, more is the charge, because charge is throughout the volume. So it says the field intensity is directly proportional to small r. Now you can go for the diagram. Here you see this is your solid sphere and this is your field axis, this is your r. Now if you see this part, here is the equation. If small r is less than capital R, then E is proportional to small r. So this is your direct straight portion, E proportional to R, this gives you. And when small r equal to capital R, then it gives you your this expression. This one is the maximum one, r rho by 3 epsilon naught. This is the maximum value of the field intensity, E max we have given here. And after that the field decreases with small r when small r is greater than capital R. So so the graph will be like this. So these are the application regarding the Gauss's theorem. So all the applications are important, and definitely every year this application used to come in your exam. So you have got 4 application. One is your field due to line charge, and another one is your field due to plane sheet, and third one is your field due to spherical shell. Maximum time spherical shell and thin sheet is very common in exam. And another one is your field due to non-conducting solid sphere, charged non-conducting solid sphere. So these are the application. I think these are the topics which included in chapter 1, and it is under the electrostatics, and chapter 1 is your electric charges and field. Now there are lots of applications or numericals are there, so you go through all the applications, and one application we are going to discuss today. It says that a charge q is placed at the center of a line joining two equal charges, each q. So show that the system of the charges will be in equilibrium if small q equal to capital Q by R. So you see this diagram, two charges are there separated by distance r. We have to place a third charge at q. Don't know how far we have to place, that's why we have considered this is your x, this is your r minus x. Now we have to define what is the equilibrium condition, or under equilibrium we have to prove that q equal to capital minus q by r. So equilibrium is possible if we consider this charge. Definitely a force will be there on the small q due to plus this charge, as well as force on the small q due to this charge. If these two forces are identical, then q will not move, so this system is in equilibrium. So if you have to consider regarding the force, then capital K q small q by x square equal to k q q r minus x square. So if you simplify, x square equal to r minus x square, so you can take off the square part, so what remains? X equal to r minus x. So if you take x here, then it becomes 2x equal to r, so x equal to r by 2. So again, there may be the possibility of equilibrium if we consider any charge. If we consider this charge, and if we calculate the total force on this charge due to individually this charge as well as this charge, and if the sum of the forces should be 0, then also it is in equilibrium. So if the force on charge capital Q by small q, then it should be your k capital Q small q by x square. And if we consider the force on capital Q due to this one, then this is your kqq by r square, kqq by r square. So already we have defined x equal to r by 2. So k capital Q, so k capital Q goes off from the expression small q by, in place of x we have written r by 2 square, and this is your q by r square. So we have used this equation 1, this equation x equal to r by 2. So if you substitute this one, it becomes your this r square and this r square goes off, 4 small q plus capital Q equal to 0. So small q comes out to be your minus q by 4. So this is all about your this digital class. So you go through all the topic thoroughly and find out the doubts if you have. Thank you.